partial fractions. So we're basically integrating a fraction where there's a polynomial on a polynomial. Okay? Now, the first thing we do, if we need to, is a polynomial division. We always want to get to the situation where the degree of the numerator is less than the degree of the divisor. So if we have to, we'll do a polynomial division. So once we've done that, we go and factorise the denominator. Now, to set it up, for every one of those factors that we find in the denominator, we want a fraction. A fraction where just that factor alone is a numerator. Because what we're basically doing is doing addition of algebraic fractions, but in reverse. You think about when we added algebraic fractions, we said, oh, how do we do this? We get a common denominator. Well, now we're saying, hey, this is the common denominator. Let's now break it up into the individual fractions. So we create a fraction for each factor. Now, if you've got a power on one of them, the way I like to do it is I'll create a factor for each one of the powers. So if it was cubed, I'd end up with three fractions: a on x minus a, b on x minus a squared, c on x minus a cubed. It's very rare we get as high as cubed. Usually squares as high as we'll see, but you never know. Someone might feel nasty one day. Now, if it's a polynomial, now when you think about it, the only other polynomial you could have is a quadratic, because everything can be factorised down to be a mixture of linear and quadratic factors. Okay? We saw that in complex numbers because of the conjugate property. We could always create the quadratics. So if it is a quadratic, then on the top, instead of just writing a constant, I'll write a linear function. So degree of 1 less. So I have to integrate x squared on x plus 1. Let's start with a nice easy one. Well, it is a quadratic on top, so I will do a polynomial division. And if we don't see it straight away, okay, let's do a division over the side. X into x squared, oh, that goes x. Minus x, yes, I can keep going. So minus 1, yep. Oh, remainder of 1. So we can rewrite our fraction. When we do a polynomial division, we can write it as quotient plus remainder on divisor. That's what we're basically, that's what we want. And we've now got things we can integrate. We can integrate the x, we can integrate the 1, and this one here's a log function. We've got derivative on function, so we get log of x plus 1 there. All right, let's try one where we actually do some factorising of the denominator. X squared minus x, simple little one. We just take out the common factor. But I've now got two factors, x and x minus 1. So my working out to the side here is I'm going to say, well, I must have come from a situation where I had something on x plus something on x minus 1, and the answer became 3 on x minus 1. This is like the equation that I've got to go and solve. Well, if I multiply everything by x minus 1, it becomes a lot neater because all the denominators will cancel. So I end up with a times x minus 1 plus p times x equals 3. Now, different ways I could solve this. I could expand the left-hand side out like we do with quadratic identities and say, oh, well, the coefficient of x squared must equal the coefficient of x squared. Well, in this case, there is no x squared, but coefficient of x must equal coefficient of x. Constant must equal constant. We can use that idea. Or we can just do some sensible substitution. Now, a sensible substitution here would be x equals 0, because it's going to make the b disappear. And so straight away I'll get, a is negative 3 when I substitute in. I suppose the next logical substitution is x equals 1, because that's going to make the a disappear. And that gets me b equals 3. So I now know, okay, a is minus 3, b is 3. So I can rewrite this as minus 3 on x. I can integrate that. That's a log function. Plus 3 on x minus 1. That's a log function as well. So I get minus 3 log x plus 3 log x minus 1. And that's how a mere mortal would leave their answer. I noticed that, hey, look, they've both got a coefficient of 3. So I can use my log laws. Look at that, isn't that nicer? I get log of x minus 1 on x. Now, the advantage of doing that, I suppose it depends what I'm going to do with this question. If I'm then going to use the integral to find something, the area, it's quicker to substrate into that one than the other one. But it doesn't really matter, I suppose. I'll usually only use my log laws if I notice the coefficients are the same, and then I can combine them into one log and do that. Okay, let's have a look at this one. No, we don't have to do a division. This one's fine. Denominator, x squared minus 3x minus 10. That'll factorise to be x minus 5x plus 2. Okay, so there we go. We set up our fractions. Multiply by the x minus 5x plus 2. Again, a simple substitution. We'll get rid of, first of all, the a, then the b, or the other way around. Which way did I go first? I've gone for negative 2. So I got rid of the a. Minus 3/7 is the b. Substitute in 5, I get 10/7 for the a. All right. So back over here, 10/7 minus 3/7. Now, what I'm starting to notice here is whenever the denominator is a linear function, every single time I end up with a log. And you got to. Because think about how I'm setting up the fraction. Constant on a linear function. The degree of the numerator is 1 less than the degree of the denominator. Got to be log. So each one of these linear factors will create log in my answer. And in this case, it'll be 10/7 of log x minus 5 minus 3/7 log. And you'll notice I stopped there because the coefficients were different. I didn't bother. I could have combined them because I could have brought the 10 in and said this is 1/7 log of x minus 5 to the power of 10. This would have been minus 1/7 log of x plus 2 to the power of 3. They then have 1/7 in common out the front, and I could have brought them in, but I thought, too messy. Won't worry about that. All right, let's have a look at this one. X and x squared minus 1. So this time we've got a quadratic as one of our factors. So I'll set it up. There's the a over x for the linear factor, but then bx plus c for the quadratic factor. Okay. This one's a little bit trickier, but I can still choose and get rid of some things. Like if I choose x equals 0, all that bx plus c is going to go away. So I can get the a. I can also combine the ideas. I could also say, hey, look, a, the only x squared in this is going to be ax squared when I expand out. You notice that? Nothing else will produce an x squared. On the right-hand side, there is no x squared. Does that mean a has to be 0? Let's see what happens. Thank you. I didn't notice the bx squared. So that's why a does not equal 0. We get bx squared, so actually a plus b equals 0. Well, if I now know a is 1, we now know b is as well. So I can combine the ideas, is what I'm getting at. X equals 0. However, there is another sensible substitution which will make the a disappear. I. So we now know about complex numbers. Let's use it to our advantage. If I make x equal I, then the a will disappear. And then over here I'll get bi plus c all times I, which is minus b plus ci. The real part has to equal the real part. The imaginary part has to equal the imaginary part. So the real part of b must equal minus 1, and the imaginary part c must equal 0. So we can use complex numbers to our advantage for a substitution there if we wish to. Well, you don't have to. You could have picked other numbers, end up with simultaneous equations, and solve that to find b and c as well. So there's all sorts of ways we could do that. But anyway, we've got our a, b and c. So 1 over x, I know that's going to give me a log 1. The other one becomes x on x squared plus 1. Well, that's also going to be log as well, isn't it? Because the derivative of x squared plus 1 is 2x. Well, I've got 1x on the top, so I've got half of that. So I end up with log x minus a half of log x squared plus 1. Whee, look at this one. I've already factorised it for us, so we've got a nice combination of a whole heap of things there. I've got a quadratic factor. I've got a linear factor, but the linear factor is repeated. All right, whee, there we go. So for that linear function, I'm going to set up a fraction for both the x plus 1 and the x plus 1 squared. And so there's just constants on top. And then for the x squared plus 1, I've got a quadratic on the bottom. So on the top, I'll put a linear function. Now, why do I do it this way? I could have done it without the a on x plus 1 and said, oh, well, the x plus 1 squared is a quadratic. So on the top, I'll put bx plus c or something like that. I could have made it a linear on top. But that's equivalent to what I've done if you think about it. Because a on x plus 1 would be the same as a outside of x plus 1 on x plus 1 squared. But what it's saving me doing is that I don't have to do any cancelling later on when I substitute the numbers in. Because there may well be, when I work out the numerator, if I just leave it as b on x plus 1, if I left it as bx plus c on x plus 1 squared, there may be some cancelling that ends up happening or something like that. So I find it easier to set up one fraction for each of the powers. All right, is there any clever substitution we can use here to tidy this one up? And the one that's, well, I know what's jumping out to me. What number do you want to sub in? What was this, sorry? -1. Why -1? Yeah, because I've got an x plus 1 factor there. That'll become 0. I've got an x plus 1 factor there. That'll become 0. I can get b straight away with -1. So there's -1/2. I think the next one I'm going to try is I, for the same sort of reason. Because x squared plus 1 will become 0 in both of these. So I'll end up with minus 2c plus 2di is I. So the real part equals the real part, the imaginary part equals the imaginary part. That now just leaves me with a to find. I just substitute in x equals 0, I think. If I substitute in x equals 0, I get 2a plus b plus d, but we've worked out b and d, so I can easily work out a from that. It turns out to be 0. All right, so what does our integral end up looking like? A was 0, so actually that fraction is not there, the a on x plus 1. Minus 1 on 2x plus, well, that's x plus 1 to the -2. So that's simply just to add 1 to the power over the power. X squared plus 1 on the bottom, what's that? Inverse tan. Inverse tan. So we have a half. Oh, well, I factorised out the half. There you go. But, oh, no, I don't want to leave it as minus x plus 1 to the -1. That looks ugly. There we go. That's nicer. So 1 on x plus 1 plus inverse tan x. Alternative way some people like to use. Okay, when you've got these linear factors, it's what sometimes people call the cover-up method. Okay? So if you want to find a, so here's all the linear factors. It's all a series of linear factors. I want to find a. What I do is cover it up. So a becomes function a, but I substitute in, but I cover up the factor that has a. So it becomes function a on a minus b, a minus c, and so on and so on and so on. So I just cover up, pretend it's not there, the factor that has the a, which was the fraction that involved a. If I then wanted to work out b, well, the factor that's involved b is x minus b. So I cover up the x minus b and substitute b in. Because obviously if I left that factor there and substituted b in, I'd get 0 on the bottom of the fraction, and that's going to cause me all sorts of problems. And you just keep doing that for each letter. Right? So let's have a look at some of the ones we just did. So if I wanted to work this one out, let's say, to work out a, I would cover up the x. Okay. Substitute 0 in, I should have said. Substitute 0 in, we get 3 on 0 minus 1, which is minus 3. In this one, I substitute 1 in. Remember, it was x minus a, we substituted in the a. X minus b, we substituted in the b. So in this case, I will substitute 1 in, but I'm covering up the x minus 1, so I get 3 on 1, and that's 3. Bingo, I've got the a and the b. So some people like to do that because it's very quick. Very quick. Let's try this one. To work out the a, I'll substitute in 5, but cover up the x minus 5. So I get 5 plus 5 on 5 plus 2. There's 10/7. To work out the b, I'll substitute in minus 2, because that's what makes that 0. Cover it up. Minus 2 plus 5 on minus 2 minus 5, minus 3/7. So if you just have a series of linear factors, it's a very quick way of doing it. It can still be expanded out to quadratics using complex numbers. can get a little bit more complicated for some. But let's have a look at the ones that we did. So a on x, bx plus c, x squared plus 1. Well, the a is going to be easy to work out because I can still use that idea of, well, I'll sub in 0, cover up the x, and if I sub in 0, I get 1 on 0 squared plus 1, so a is 1. Okay, so that's all right. X squared plus 1. Remember, the idea was substitute in what makes it equal to 0. So if my denominator is x squared plus 1, if I substitute in I. So if I substitute in I, cover it up, what do we get? Well, we get bi plus c is 1 on I. So bi plus c is minus I, so b must be minus 1, c must be 0.
Would you have to sub in negative I as well? Because I can do the same answer.
Would it? Well, let's have a think about that. If you subbed in minus I as well, you would get what? Minus, but it would have to be the same, wouldn't it? Because this is going to change to minus bi, but this is going to become 1 on minus I. And the c, well, 0 doesn't matter, so it would give us the same answer. It just seems more logical to use the positive of that. All right, let's have a look at this one. We didn't do this one, but let's just apply the idea. Well, finding the a would be simple enough because it's a linear factor. I can just say, well, let's make x equal to 1, cover up the x minus 1, and I get a is 1. 4x squared plus 1. What makes that equal to 0? Well, x squared is going to have to equal negative a quarter. So if x squared is negative a quarter, x would be a half I. That's what I say, sometimes it might get a little bit messy if you want to do it this way. So, okay, if we sub in a half I, so bx plus c becomes bi on 2 plus c. Sub in the I on 2. You see what I mean? Might not be a fantastic technique for this type of one, but let's just keep going with it. Here we go. Eventually I can get there. Do a bit of realising the denominator. 1 minus 3 on 2i. So I now know that b is minus 3, c is 1. You might prefer the more traditional methods for that sort of one. What about if there's multiple factors? So remember we had ones where we had x plus 1 squared. Just a little bit. Little, I should have put it in. A little bit more work. Let's have a look at something like this. All right, working out a is going to be easy enough. A turns out to be negative 2. Working out b, is that going to be easy or hard? Let's see. B is going to actually be hard. C is actually the one that's going to be easier because the factor matches the denominator over here. So we always go with the higher power because that's the one where the factor is going to match it. And if that works, we can just do it the same way. So C, I can work out. I'll just make x equal to 1, cover up the x minus 1 squared, and I get 9, C is 3. B is the problem. All right, well, I'm just going to do it by simple substitution then. Why worry about it? Like, I've got other techniques I can use. So for the b on x minus 1, I'll say, oh, well, the x equals 0. Easy enough number to substitute in. And at this stage, I've still got it as fractions, but I still get the answer. B ends up being, eventually, there it is, b is 2. Now, of course, if that power was higher than 2, I would have done the cover-up method for, say, cubed, but then I might have to do a couple of substitutions to get the other 2. It just gives us an alternative way of doing things. Ooh, what about this one then? So I've got x plus 1 and x plus 1 squared. Oh, and I've got, x squared plus 1 as well. Ooh. Well, I can work out the b. The b is going to be the easy one in this one, isn't it? So b is minus a half. Okay. I can do the ci plus d because I can substitute in x equals I A little bit of work to do there, but I get CI plus D is a half. So all right, C is 0, D is a half. So I've got B, I've got C, I've got D. I just got to work out A. I'll just make X equal 0. Again, easiest number to substitute in, so let's do that. I get A plus B plus D is 0 when I substitute that all in. And so I get A actually turns out to be 0 in this case. What about if you've got a quadratic denominator that can't be factorised? So you've got x squared plus 4x plus 5, and I want to try the cover-up method. This is where it gets real tricky, because again, the idea is, what makes the factor equal to 0? Well, if x squared plus 4x plus 5 can't be factorised, what I'm going to substitute in is going to be rather interesting. A is easy to work out. I can do that. Okay. I can complete the square to work out the appropriate substitution. X squared plus 4x plus 5 is x plus 2 squared plus 1. So how about I let x equal minus 2 plus I? I'm sure it's what you thought of straight away as well. So if I use the cover-up method, and I'm going to let x equal minus 2 plus I. And so there we go. We got b times minus 2 plus I plus c is 2 on minus 2 plus I minus 1. And it comes down to, there it is, minus 1 minus I. So b is minus 1. C turns out to be minus 3. Now, again, I'm not suggesting that maybe this is the best way of doing it. Most times when you see, not all books look at this cover-up method. I think Terry Lee's a fan of it. I think it's in his book. I don't think it is in the Cambridge, I'm not sure. But they tend to just stop at linear factors. But I don't like that. I don't like methods where I go, well, okay, I can only use it in this situation. That's why I've added this extra bit in, because I wanted to flesh this out and show, oh yeah, I can still use the idea when it's not linear factors. Might not be the greatest technique for those ones, but the idea will still work if you really want to pursue it and go down that path. Okay, so Patel 2G and our Cambridge. Sorry to confuse you all that there. Cambridge.